Okay, so the context that we're going to be looking at in terms of iterative solvers is going to be to solve partial differential equations. So I'm going to solve, we're going to take a partial differential equation, turn it into a linear algebra problem, and then the iterative methods are going to be used to solve that linear algebra problem. So to get to that point, we first need to know a little bit about PDEs and how to model them and things like that. Now, this is not a PDE theory course. I'm not going to talk about regularity of solutions and all of these sorts of things. I'm just going to derive common partial differential equations that sort of model common phenomenon. And I'm going to begin with something called a conservation law, and everything is really going to be based on this. So conservation law which sounds, maybe like something that it isn't. This isn't some sort of like ecological law or something like that. We're talking about a quantity that is conserved. So I'm going to be very vague with how I describe things because this sort of paradigm that I'm working in covers a lot of different specific cases. So we're going to look at first in the one-dimensional case. So what I mean by this, we have some some one-dimensional thing here. It could be a pipe. Okay, I know a pipe is 3 dimensions, but imagine a pipe, you can just flow this way and that way, right? There's just 2 ways of flowing, this way or that way. We're not flowing up or down, and we're not flowing this way and that way. So that'd be one thing that we could model kind of as one dimension. Another thing we could model, well, there's other things we could model as one dimensions as well. So, and I'll get to that in just a minute. So that's what I mean by one-dimensional. We're going to say that this is at the point 0, and this is at the point L. And for the derivation of the PDE, we can either think about there being like caps here, so it's a finite length thing, or we can sort of model it as an infinite length thing going off in this direction here. Okay, so we're interested in modeling u of xt. So what is u of xt? U of xt is the concentration of stuff. Okay, so I told you I was going to be very vague here. It's a concentration of stuff at location x and time t. So u of xt is the concentration of stuff at location x and time t. Now, what is stuff? Well, it depends on what we're modeling. Maybe we're thinking about this as being a pipe filled with water, and we drop some dye in it, and we want to see how the dye disperses through the pipe. And maybe even there's water flow moving this way that's also moving the dye along. Maybe this is a river, and there's a factory that pollutes here, and we want to see how that pollution spreads out and disperses and diffuses as it moves along the river. Maybe this is like an air duct system in a building like the one that I'm in now, and some evil person places poison there. We want to see how the poison spreads out. I don't know why my mind is going to pollution and poison so quickly. Maybe this represents a road. And, so before maybe the units were like the number of dye particles per meter. Or maybe the units were something like the number of poison droplets or whatever per meter. The amount of pollution, kilograms of pollution per meter, whatever the appropriate units are. But maybe this represents, maybe we're modeling traffic flow. Okay, and so this is like a segment of a road. And maybe we're modeling something like U is going to represent the number of cars per meter, the number of cars per mile would probably be something that would make a little more sense for those units. Maybe we are modeling how crowd control can happen and how crowds move, or modeling the evacuation of a building. And this represents like a hallway or something. And then the units are going to be the number of people per minute. Maybe this is a solid pipe, and U represents the concentration of thermal energy per minute. This is sort of the classic heat equation. And then from there, we can sort of connect the heat directly to the temperature and get what really is a classical heat equation, which is the model of the temperature of the rock. Whatever it is, we have some concentration, and as I just sort of went over a lot of different examples, you can probably come up with other examples as well. This could be the beginning of a model when you want to model like blood flow in your arteries and veins, but there's complications because this can get your arteries get smaller and bigger depending on blood flow and things like that. Okay, So u of xt is going to be the concentration of stuff at location x and time t. And again, I want to keep it purposely vague, or I'm keeping it vague on purpose, just because this is a paradigm that covers a lot of different things. Okay, the next thing that we're going to look at is f of xt. Okay, so let me just give you, let me just write what the units here are going to be for you. Sorry, I meant to do that before. This is going to be like the amount of stuff per meter. Okay, so I'm going to keep the length units as meter, the time units as seconds, but the stuff here is going to depend on whatever it is we're modeling. So f of xt is going to be the amount of stuff flowing to the right at time t and location x. Okay, so I want to point out a couple of things here. It's a vector quantity. I'm writing it as a vector quantity, not because it has two different components or things like that, because I really want us to get to thinking about, even in the one-dimensional case, that this has a direction. So it has a magnitude, which is going to be its absolute value, and then its direction, which is either going to be plus or minus. So it's flowing to the right. When we look in 2 dimensions, it'll be a proper vector. Okay, and so the units here is going to be stuff per second. Okay, so it's going to be stuff per second. Okay. And now I want to derive a differential equation that relates these two things together. Now, one important thing that I haven't said before is that we are assuming that for u of xt, that it is called a conserved quantity. That is, it is not popping into and out of existence by itself. Now, that doesn't mean that there can't be sources acting in the pipe, adding this to the pipe, or sinks taking it away. Okay, maybe if we're modeling pollution, we put a pollution filter, and the pollution filter will take things out. Or maybe, we are modeling the continual dumping of pollution into this, so we have a pollution source. Things like that, right? But it's not something that's just going to go into or out of existence by itself. All right, so we're going to look at a representative sample of this one-dimensional thing here, pipe, road, whatever it is, river, and we're going to call this location A, and we're going to call this location B. Okay, and we're first going to see what happens when we don't have the presence of any sources. Okay, so we just have whatever quantity is in the pipe or the road or the hallway or whatever it is, that's the quantity there, and none is being added or subtracted. Okay, so when we say that u of xt is the concentration of stuff between A and B, what we mean, I'm going to use this notation here, A of t is the amount of stuff from A to B is given by the integral going from x equals A to B, u of xt dx. U is a concentration. If we just match up the units, u of xt, you has units of stuff per meter, dx has units of meter, so overall u of xt times dx is stuff per meter times meter, which is stuff. So the units match up here. But this is exactly what a concentration or a density is. If you integrate a density or a concentration between 2 points, it tells you how much of that stuff is between those 2 points. Okay, and what we want to do is we want to see how this is going to change with time. So notice u of xt is a function of the variables x and t, but when we do this integral, the x goes away, and it's just a function of the t variable. So I can take an ordinary derivative over here, and what we're going to get, this is going to be the ordinary derivative on the outside. Okay, but now we're going to make some assumptions about u, in particular that it's continuous. And we're integrating over a bounded domain, so then there's no problem with swapping the integral and the derivative around. Okay, and more, this is a typical thing that we do. We're going to sort of assume that the solution has, or that the thing that we're modeling kind of has some nice properties, and then later on we can see what happens if it doesn't have those nice properties. Anyways, we're going to interchange these two. Okay, if you don't care about having to justify that, then you don't even need to know about continuity or not. But now when the derivative goes on the inside of the integral, u is a function of the variables x and t, so now the ordinary derivative is going to be a partial derivative, and it's going to be the partial derivative of u with respect to t, xt dx. Okay. So now let's think, this is just an expression for the rate of change of substance in this segment from A to B. Now let's make sure the units match up. So the unit should be stuff per second, right? That's what the A is, the amount of stuff, so its time derivative should be stuff per second. Let's see what we get over here. Well, U has units of stuff per meter. You take a derivative, you get stuff per meter per second. You multiply by meters, that gives you stuff per second, because the meters cancel, and so the units here are correct. Okay, but what is the only way that the amount of stuff in this can change? Well, it's either going to be, flowing there, or flowing here, or flowing there, or flowing there. In other words, it's going to be given by the flux at these boundaries here. Okay, so another way that we can model this. Okay, now remember, F is the amount of stuff flowing to the right. So this is going to be the rate flowing into this segment minus the rate flowing out of this segment. So rate in minus rate out. This is given by F of AT minus F of BT. And let's think about this for a second. If F of AT is positive, it means we are flowing to the right here, and so this contributes to the rate in term appropriately. If F of AT is negative, it's going to be flowing to the left, or if we have flow to the left, it's stuff moving out at this boundary here. So the way that I've drawn my arrows here, it might be a little bit confusing because along this boundary is only doing one thing. I was just drawing two arrows to indicate that it could be all going this way, it could be all going that way. Okay, so we have something like this. Now, if we have flow to the right at A, that's going to be increasing the amount of stuff in this interval here. And if F of AT is positive, that contributes to the rate in. If F of AT is negative, that means we're flowing to the left. It means stuff is flowing out at this boundary point A, meaning this is negative, so it's contributing to the rate out. And similar things can be said for F of BT here. Okay, but now anytime we have a difference of things like this, we can always write it as an integral using the fundamental theorem of calculus. So this is equal to minus the integral from A to B times the x derivative of f. Like this. Okay, and again, let's make sure that the units are here. The units here are correct. So f has units of stuff per second. We take the x derivative, that's stuff per second per meter. We multiply dx, which has units of meters, and overall this now has units of stuff per second, which is what we needed to have. Okay, now notice what we're saying. We're saying that these two things are equal to each other. Okay, and I'm going to write that this purple integral is equal to that blue integral. And I'm going to erase all of this and just write that down again. So what we're saying is that the purple integral is equal to the blue integral. The purple integral is the integral from A to B of the partial derivative of u with respect to t. And this is equal to minus the integral, let me write this in blue as well. This is equal to minus the integral from A to B, the partial derivative of f with respect to x dx, like this. Okay, now we can rearrange this and have this, have this all be in one integral. And when you combine this all into one integral, you get the following. Find a marker. Now, if we combine all of this into the following, I'm just going to write this as one integral. And this is going to be the integral from A to B. I don't know why I am so committed to these colors, times the partial derivative of u with respect to t plus the partial derivative of f with respect to x. Gotta go back to black if I'm going to stay consistent here. Dx is equal to 0. Okay, so here's an important observation. There is nothing special about the points A and B. This works for any segment of this for any a and b, okay, as long as a is less than b. So what we're saying is that this function here, its integral is equal to 0 over any interval. Now, anytime you have a function whose integral is equal to 0 over every over every interval, one of two things happens. One of two things happens. Either the function is 0 everywhere, or it is discontinuous and it's 0 almost everywhere, but except at some isolated points. So however you want to interpret it, what it tells us is that this function is equal to 0. In other words, this is equal to 0. Okay, now this is a differential equation that relates the unknown U concentration to the unknown F, which is the flux. And as I had before, we have that as well. Now, in the presence of a source or a sink, we get another term right here. This is f of xt. And this is either a source term, so maybe we have somebody just dumping in pollution right here. So maybe you have somebody dumping in pollution right there. We can model that with an external addition of pollution there, or maybe even better, it could be a sink, and we have some sort of pollution filter here, and as the pollution passes through here, it gets filtered out, and so it goes away. So now in this case, there's 3 different ways pollution could leave this segment here, or the pollution could change here, through flowing at the boundaries A and B, or by getting sucked out through the pollution filter here, and that's what this would represent. Okay. So we have this equation. This is called called a one-dimensional conservation law. Now in 2 dimensions, the derivation is very similar to this. So I want to go over the derivation for this in 2 dimensions and just right now. So in this situation, it gets a little more abstract, and we've got to use some vector calculus. But again, we're going to be looking at a 2-dimensional thing right here. So a 2-dimensional box right here. And it could extend out this way, this way, this way, this way. It doesn't have to be a box. It could be a more interesting shape, and typically is a more interesting shape. But what we're going to do now is we're just going to take an arbitrary region like this with a smooth boundary. I'm going to call it omega. Now the things over here are going to stay largely the same. U of xt is now going to be U of xyt. So it's going to be the concentration of stuff at location xy. So maybe I can write that in red so you can sort of track where the changes are happening. Here it is. Location at xy. And the units are going to be stuff per meter squared. Over here, the only difference is going to be, we're going to add, it's going to be the amount of stuff flowing. And it's not really to right. F is going to be a legitimate vector now. Okay, so it's going to be the amount of stuff, y here as well, so xy. It's going to be like a legitimate vector quantity, a 2-dimensional vector quantity. The magnitude indicates the speed of the flow, and then the direction indicates the direction of the flow. Okay, and similar to what we did before, we're going to say that A of t, we're going to fix a region for now, but again, it's important that it's arbitrary. A of t is going to be the integral over the region omega of the function u of x, y, t with respect to the normal area integral. And then if we do something like we did before, we take a derivative with respect to time. That tells us how the change is. We're going to get a prime of t is equal to the double integral. I only had a single integral before, which is not wrong, but maybe it's a little more common. Try this as a double integral. And then we're going to get the u derivative of t x y t dA like this. Okay, now what about the flux? Well, what are we going to do with the flux? So this tells us how the quantity of stuff in this is changing with respect to time. Again, if we don't have any sources or sinks, that is the amount of stuff that's in this whole area that we're modeling is fixed, we just want to see how it moves around. That's what we did with one dimension. Then for a fixed region right here, the only way that things can enter or leave are going to be through the boundary here. So maybe at this point right here, we have a flux that looks like this. Now, to this flux, we can decompose this flux into two different directions. One is going to be normal to the boundary, and one is going to be parallel to the boundary. So one is going to be perpendicular to the boundary, one is going to be parallel to the boundary. The part of the F vector flux that is flowing parallel to the boundary, that's not causing any stuff to flow in or out of the region. It's only the part that is perpendicular to the boundary that is flowing in or out of the region. Okay, and so what this tells us then is, got my colors reversed from how I was doing it before, but that's okay. A prime of t is equal to minus the integral around the boundary of omega of f dotted with the normal vector. And we'll say we're integrating with respect to s. So the reason it's minus is because the normal vector is taken to be the outward pointing normal vector. And so if that is positive, if f dotted within is positive, it indicates flow going out, so we need it to be negative. Okay. Now, using the divergence theorem, this is equal to the integral of omega of minus the divergence of f. Okay, and if you don't remember what divergence is, please try to remember what it is. But we have this vector, this gradient vector, which we can think about as being a vector of like operators. And so we're going to have the partial derivative, the partial x derivative operator there, the partial y derivative operator there. It typically speaking, things like the delta here and the nabla, which is the triangle going the other way, are differential operators that operate in the spatial variables, not the time variable. Okay, so we're going to dot this with our f vector, which I'm just going to call let's say f1 and f2. And then the divergence, the dot product notation here is suggestive. What does the normal dot product do? It's that times that plus that times that. It's going to be very similar here, except times just means do the operator. So it's going to be the x derivative of f1 plus the y derivative of f2. So it's going to be the x derivative of the x derivative of f1 plus the y derivative of f2. So that's just what divergence means. Okay, so now we can do something very similar to what we had before. These two integrals are equal to each other, and if we add them together and move things around, we get the following. Okay, we get that the integral over omega of the partial derivative of u with respect to time plus the divergence of the flux dA, this is equal to 0 for all smooth regions omega. And again, something similar is going to be true. The integral of this function over all smooth regions omega is equal to 0. So it means the function is either is either 0 or it's discontinuous, and it's going to be non-zero at some isolated points. And so we're going to get the two-dimensional version of what we got before, the u derivative of t plus the divergence of the flux is equal to 0. Okay, so we have these two different conservation laws. I'm going to write them up here. If you want to state it in explicit one-dimensional formula, it's going to be that the t derivative of u plus the x derivative of f is equal to 0. And maybe to cause less confusion, hopefully, I'm just going to keep that as f and not write it as a vector. And then this is one dimension. And then in 2 dimensions, we're going to have the t derivative of u plus the divergence of the flux. And here I will write the vector there, the arrow notation for f, simply because it is a legitimate two-dimensional vector here. Okay. And this is the two-dimensional version. And in fact, this is the n-dimensional version. If f is an n-dimensional, if you're looking in three-dimensional space, f would be a three-dimensional vector. This would be the three-dimensional gradient vector as well, and so on and so forth. Okay, so this is really the n-dimensional case, but we're only going to be dealing in 1 and 2 dimensions for this class. And I just want to point out, one other thing. We can also add, for both of these terms, we can also add a force term, or not a force term, but some sort of external source or sink term. Okay, so I want to point out that these things are true no matter what we're modeling, as long as we're modeling, a quantity of something that is conserved, which is going to be basically everything that we're modeling. As long as we're modeling something like that, these are going to work out. Now, for both of these equations, this is one equation and two unknowns, u and f. This is also one equation and two unknowns, u and f. So to make sense of this, to be able to sort of solve this in any meaningful way, we have to be able to give one more equation for both of these two things. And we'll do that in the next video. There's different ways that we can relate. We need another way to relate these two things, basically. And there's several ways that we can do that. I'm going to show you one way in the next video, which is going to be the primary thing, the primary type of problem that we model in this class.